Hi and welcome to another episode of TRX Bench. Today we have here really a very exciting amplifier on the bench. So it is an early solid state amplifier from Transworld. It is a TW-500, so it is a 500 up to 600 watt PEP amplifier, and in these days normally tube amplifiers were very common. So yeah, it is really exciting because it is running on 14 volt DC, so that means this amplifier really needs a lot of power, so up to 70 amps or so. And well, there you see already why it is exciting, because in these days with normal transistors, so bipolar transistors, we had to use low voltages, because all these power transistors are not able to manage high voltages as it is today. So our modern MOS-FET transistors are able to handle up to 500 volt, and therefore it is very easy to produce high power. But in these days, when the first solid state amplifier has been built, so you really had to do some tricks to get out a lot of power. And let's look into the amplifier and discuss a little bit how it works, and then you may understand why it is so exciting. And and of course there's a problem with the amplifier, and that is what we want to look after. So it came in with quite high power, which the amplifier is drawing in idle mode. So that means when you press PTT, then it will switch into transmit, of course, and then it already, without any modulation or so, it will already draw 20 plus amps. And yeah, that is what we need to look after and see what's going on, and if we are able to repair this amp, because if there are transistors blown, then it is really very expensive, because one of those power transistors is around 50 bucks, and this one has 8. So it is really exciting. So let's look into it and let's see what we can do. Alright, and here we have it, and you already see not many knobs here on the amplifier. So only here a big current meter up to 100 amps DC. So that is telling you what the collector current currently is if it is in operation, and that's it. So this amplifier has an automatic switching for the different bands over the radio, which should be connected here to this amplifier. And this amplifier is something with has to go into a rig or so. It is not a desktop amplifier. So very nice. Let's have a look into it. Okay, and here is our amplifier. So here our low pass filter board. So that is quite normal, as we know it from all the other amplifiers as well. So no difference between a tube amplifier or a transistor amplifier. And here on this side we have, of course, our power amplifier itself, and underneath we have our power supply and our cooling. Okay, and here we have the chance to look a little bit underneath. So of course here we have the heatsink, which goes here under our complete low pass filter board and amplifier board, and we have here our power transformers, and we have 4 of these power transformers, and you see here the big rectifiers connected to each of the 4 transformers here, net transformers, and of course you see here a massive electrolytic capacitor to filter the rectified voltage. And here a view from the other side, and again here is another huge electrolytic capacitor, and you see down here the fan for cooling here the heatsink, and well, then of course we have here a little bit of power line distribution and whatever. And yeah, this is here only here our amp meter, so that is nothing special, so that is not so fault. And yeah, so you see it is really an interesting design. Okay, and here we are finally looking at the amplifier section. And what we can see here first is that we really have 8 transistors, a so-called 8-pill amplifier, and that already shows how this had to be handled these days. And well, yeah, today we still have CB radio amplifiers built in the same manner. So in the United States, Texas Star was a very known brand for, yeah, normally this Texas Star amplifier were 10-meter CW amplifiers, but they have modified and used on CB radios, and yeah, with a 8-pill amplifier and, you know, powerful net transformer, you were able to get 2 kilowatt or even more out of a 8-pill design. So that is still very well known in the CB world. Well, in the amateur radio world, it has changed a little bit, as I already said. With MOS-FETs we can use much higher voltages, and it is much easier to get high power out of a design. And what you finally see here is, so if you like, all these portions here are individual amplifiers for itself, and to get out a high power, this amplifiers has simply been set in parallel, and that is a way how to get high power out of it. And therefore you had to do some design, special design steps, and that is first of all, if you see this here, so this is a splitter, because when you get here into our amplifier, you need to split your 50 ohm impedance over a splitter like this here into, in this case, 4 portions of 50 ohm ports, and you can see it here. So we have 1, 2, 3, 4, and that means we are able to deliver to each of our amplifier portions, or let me call it individual amplifier, we have to deliver a 50 ohm port to the dedicated broadband input transformer, because this here of course are the broadband input transformer for the amplifier module, and the bigger ones here, this here, are the output transformers. And so we really deliver our input signal equally to each of these 4 amplifiers, and they amplify, you know, the signal in the same manner. And in our case, this individual amplifier will be able to produce 150 watt PEP output power, and that means 150 watt times 4, and we have then 600 watt output power, and therefore we have to do, of course, exactly the same at the output of our broadband transformers, because we have now here our output power, and now we have to combine it again back to one port, and of course this one port is then 50 ohm, because we want to connect here again our load, and of course our load is our 50 ohm radio antenna, and therefore we need to get finally back to 50 ohm. So that is what it is all about, and therefore we have to combine it, and that is, as you already can see, the design what has been chosen, simply due to the fact that this power transistors, the bipolar power transistors, NPN power transistors, are not able to handle high voltages, and therefore this efforts needed to be done to you know, produce finally high output. And I mean, this here is really developed very carefully, so only 600 watt, so a lot more power could be get out of this construction, but we are limited here by our power supply, because we only have 70 watt, and to get much more power out of this design, we definitely need over 100, maybe 150 amps, which needs to be supplied here to our amplifier section. So therefore, you know, these days this design is not state of the art. So MOS-FET transistors are less expensive, and they are really able to handle high voltages. And since power is equal to voltage times amps, right? Since that is the fact, we need high power and high voltage to get high power. And if we only have low voltage, you may understand that it is difficult to get high power out of one section. And with simply MOS-FET amplifier, you only have 2 pillets, and you can get out of it, maybe with the right heatsink, 1 kilowatt. So that is how we can do it today. So okay, I guess this is enough explanation how it hangs together. And now let's look after the problem. As I told you, this amplifier is producing a very high, it looks like a high bias current. So yeah, I'm not really know if it is high bias current or if we have maybe a shorted transistor already. So that is what we need to investigate. Yeah, or we have really a problem in our bias circuit. So that is what we need to find, and we go very carefully here into the circuit, not to destroy anything additional what already is wrong here with our design. Okay, so let's start troubleshooting, and first and that is a visual inspection, and these little 10 ohm resistors which are here connected to our design are already an indication if a transistor is blown, but as far as I see, we do not have here blown 10 ohm resistors, so all looks quite nice, and that is definitely a good sign. So before we hook power to our amplifier board, I will do a quick test. I mean, that is not completely telling us what's wrong, but it might give us an indication. Okay, and our first test will be if we find directly a dead short. You know, you definitely can't test transistors in circuit, so you only get you know, a rough indication, but that is nothing reliable. But what you can see is if there is really a dead short or not. All other information really can't be used. So when I go now here into it and check between base and collector, I see I have 33 kilo ohm, and I can do that, of course, with all transistors, and if I get more or less same result, then that is of course a good sign. But yeah, as I said, you really can't rely on this test procedure. So it is, yeah, as I said, just to see if I can directly see something very much wrong, and it looks like that there is not directly a dead short here, and that is of course not bad, but as I said, it is only a rough indication. The next step, what we're gonna do is we switch the amplifier on, and with my adjustable line transformer, I gently increase the voltage to see if we see a breakdown, and we directly see a breakdown if we see excessive power which is drawn, and that will be yet now our next step. Okay, and my power analyzer will tell us what's going on here. So when I'm cranking up the voltage, we will see the AC voltage into our amplifier. We will see the watt which the amplifier is consuming, and of course we can see the amps. That is all on the AC side. But anyways, if there is somewhere a short, we would directly see that we have an excessive power consumption, and that then will lead to, you know, another troubleshooting method, because then we need a different way. Okay, so that means we switch it on, and it can't glow, that is for sure. And this is here our DC breaker, and we switch it on, or we reset it, whatever we want to call it. And now I start cranking up our voltage, or AC voltage, and we observe our drawing arms. Okay, so let's start, and yeah, you directly see that the AC amps are getting up, and watch here our amp indication and our watt indication. So normally under this condition, the amplifier should draw very low current, so really not too much. And so let's see what will happen here. 62 volt, 4 watt, so that is just fine. And you can see here that our LED starts glowing. Oh, that means up to now everything is fine. And let's go up. So since we are here in Europe, we have 230 volt net voltages, and therefore we crank it up, of course, up to 230 volt. And therefore, let me go up, and always see it checking our amps. But up to now 10 watt, 80 milliamps, so that is just fine, no problem whatsoever. And I will increase it. Looks fine, no problem. I mean, that is already a good indication, because we really do not see much power drawn, and that is very promising, to be honest. So okay, let's go to, that's enough. That is definitely enough. So our system is drawing 28 watt, that means 370 milliamps, and that is just fine, no problem whatsoever. Our next step is, let's check if the voltages are present at our transistors, right? Okay, so you should see what I'm doing. Now I'm really interested if we have our supply voltage at each of our 8 transistors, and if we can read it, then it is the next good indication. So let's start here at the last one, and yeah, we have 18 volt. That is another interesting fact with this amplifiers. So these amplifiers do not have a regulated power supply. It is only the transformer, the rectifier, in this case for bridge rectifiers, and a filter capacitor. So that's it. This can be done as long an amplifier like this has bias current adjustment, because then you really do not need to be worried about not having a regulated power while the amplifier is used. So with I don't know, 500, 600 watt, then of course the voltage will drop to, I don't know, 14 volt. And that is fine, because you really do not need to handle an expensive power supply electronic. So it is easy as it is, only transformer, rectifier and filter cap, and that's it, fine. So therefore we read now approximately 18 volt here, and that is normal, and we should see it at each of our collectors. And let's go through here our 8 collectors, and it's looking good up to now. Okay, and one here, and the last one is here. For the moment in time, we should not see any bias voltage at the base of the transistors, because bias voltage is only supplied when PTT has been pressed. So therefore, if we go now down here to the base, we see nothing, and that is exactly what we want to see, because transmit has not switched so far, so everything looks good here as well. Just want to make sure that there is not something leaking through, but it is not, and that is just fine. Okay, so you know that now makes the situation a little bit better, because I believe that we do not really have a blown transistor, because as I already said, these transistors are very expensive. So these are 310022. I believe it is something similar to a MRF 455 or such. I believe that these transistors are obsolete. I do not believe that we can get these transistors, and therefore that is good, because otherwise, if even only one would have been blown, we really would need to replace a complete set. And yeah, so that is then a complete different story. Okay, now our next step is we need to see if, when we engage our bias circuit, and again very, very carefully and slowly, we need to observe the power which is going in our amplifier. So that will be the next step, and therefore I of course use here an amp meter, and I can easily clamp it here to our plus lead, and now we are able to watch here our power supply, our power which is drawn. So that is what I wanted to say. So now let me connect via an external power supply our bias circuit, and bias circuit is more or less down here. So this here all around is our bias circuit, and now let's that take into use to see what will happening, you know, with an upcoming voltage here to this resistor. But yeah, first let's have a look into our schematic to understand what I'm trying to explain here. Okay, here is our schematic, and down here we have our power supply, just fine. And you see, if I zoom in a little bit here, you see here our bias circuit, and yeah, it consists here of this two transistors, and if we follow here along, you see that over here our transformer, our bases are supplied with, once again, if we follow here along over our transformer to the left side, over this way to the base, right, and here over the right side to the second transistor, and that is the same to all of these transistors here. So we need to have a bias voltage which will set our transistors to a voltage below 0.7 volt, okay, and we will have then a current flow over our collector to emitter to ground, which is the bias current, and when we give a little voltage to the base, then we can adjust this idle or this bias current, and according our service manual, we should adjust our bias to 3.5 amps without any drive from our radio. So that means we only switch to transmit, right? And then we should see, without any drive, we should see a bias current of 3.5 amp. And that is what we need now to check. But I do not want directly switch the amp in transmit, because then I would directly get full power here to our transistors. So therefore I use this 8 ohm resistor, and I connect here an external power supply, and I start with 0 volt and crank it up very slowly, and let's see, because if we follow here, so this here, by the way, is receive transmit switch, and if the radio goes into transmit, then this switch here will flip over, and we will, let me see if we can follow here our line. Let me see, I do not have it digitally, so it is a little bit more critical, but anyways, if we follow here this trace, we finally get down here to this point, right? And at this point here we should see 18 volt, so that is exactly the same voltage we have already seen at the collector of our power transistors. And when the radio get set into transmit, then this 18 volts will be directly here at our resistor, and will deliver a voltage to our basis to create our bias current. And I do not want to get it fully switched on, so I carefully will increase our voltage and then see what happens. Okay, so far we have all prepared. So I have here our external power supply connected here to our power resistor, which will feed here our bias circuit. Okay, and now we can really see both. And remember, normally we will have 18 volt here at our power resistor, so that is simply the output voltage of our power supply, which might drop to 14 volt under fully load. But in or under no drive condition, we want to have a bias current of 3.5 amps according our service manual, right? And yeah, so we can now here observe our power, which is drawing by our amplifier, and we should not see more than 3.5 amps while I'm increasing here my voltage from the power supply. So let me simply start, and let me increase here my voltage, and let's see what is that was of course wrong, because my power supply is not switched in. Now it is switched in. Okay, let me check, and now once again the procedure. Let's start, and now you can directly see that we have current, and let's observe here our main power amp meter, and okay, 4 volt, 5 volt, 6. We have already 1.3 amps here, 2 amps, oh, 4 amps, and with 10 volts, so that is already too high. And now my meter here switched off. Okay, once again, wrong time. Nice. Okay, once again the same procedure. Let's go down. Let's switch the supply on, and again let's go up here and see. 10. Yeah, we are here increasing 8 amps, 10 amps with only 14, and that is definitely wrong. So let me switch it off. So that means that we might have here a problem in our bias circuit, because we should not see 10 amps with only 10 or 11 volt. So something must be wrong here in our bias circuit. Okay, and down here we have our bias control to adjust our bias current. So let me see if something will change when I'm turning here this pot. Okay, and let me go down here a little bit with my voltage, and you can't see here the meter very good. Okay, so let me switch it on, and we see 4 volt and nothing is happening. Okay, so let me increase it a little bit here, that the amp is really starting to draw current. So let me not go over the limit, so 3 amps with 9 volt, fine, so nothing should go wrong with 3 amps. And now let me see if I can, oh holla, I'm just touching here the pot and it is jumping. Oh my goodness. So let me do it like this. It looks like that the pot has a problem. So let's see. Whoa. So it is jumping. It is really jumping. Let me turn it down here, and it looks like that the pot has a problem. So let me switch off here my power supply for a second, and let's move it here. So this is a wire pot, and that can be already the problem, that our pot here is somewhat oxidized, and you can hear it. It is a wire pot. You can really hear it, that the contacts inside are scraping here over the wire, and if this pot is dirty, then of course it can't work, of course. So okay, now I close it, and let's go ahead. Okay, so now let me switch it back on, and I have set it to the lowest possible setting, and we have 9 volt. So let me go up to 18 volt, because that is of course the voltage which will be at our resistor here. So that is a normal operation condition, and now we have a bias voltage of 2 amps, and we are requested to set it to 3.5. so let's see if that is possible, and it is obviously. So moving it back and forth seems to help a little bit, but I will clean it with dioxide spray, of course. So now I have 3.6 amps bias current with 18 volt, and we are drawing here over our bias circuit half an amp. So that looks healthy, and we can see our current as well here on our DC amp meter. So that looks quite nice. So it is 2, 4, 6, 8, 10 amps, and we are close to 4, and that is more or less identical what we see on our clamp meter. So it looks like that our drive power is now just fine. Okay, I've cleaned the pot extensively with here my trusty contact 60, which is a dioxide spray, and afterwards I'm always clean it with contact WL, which will finally wash our contacts as good as possible. And that has been done, and now I just want to wait until it has completely dried, and then we try to take the amplifier back in service, and if then with an external power supply we will still have our 3.5 amp bias current, then we can start testing the amplifier with an exciter radio. Okay, and I have here connected to our remote socket. I have here connected a diode just to be able to simulate the PTT switch, which means that when I take now here the other hand and put it to ground, then our transmit receive relay should switch, and we should be able to read our bias current. So let me see, our amp is switched on, and normally if I put it to ground I should be able to switch to transmit, and yeah, we should see our current. But let me reposition the camera that you can read, of course, our amp meter. Okay, so that way it should work. And now let me connect here our PTT to ground to switch our transmitter relay. And yeah, it is switching, and we see we have a bias current, but it is now much lower than we have it adjusted to. So let's have a look into our schematic, but first of all let's undo here this. Okay, so here's our circuit, and down there this is PTT, so that is pin 10, and we see here our relay, which needs to set to ground, of course. And let's see how our relay get supplied, and okay, I see it, and that makes sense, of course. Our bias voltage is always kept on regulated voltage, and you see here our little voltage regulator. It is a 12 volt regulator, and yeah, so that makes sense. So now we have a completely lower voltage at our resistor, so it is not 18 volt, it is only 12 volt, and therefore it is clear that we have here a different bias current, so we need to readjust it. Okay, so let's double check. So we have it set to transmit, and let's read here the voltage at our resistor. So you can see it. So it is 12.1 volt. So obviously it is really going over the voltage regulator, but that then must be a correction, maybe in the circuit, or something has been drawn wrong here in our schematic. Let me show you what I mean. Again, when I'm zooming in here, you can clearly see that here is our PTT switch, and we have here our relay, and that is the coil of our transmit receive relay, of course, and you clearly can see that it is supplied here out of our 12 volt regulator. But different to what we have seen here on the board is, so we measured at our bias circuit over here. Let me zoom in. So we measured here at this resistor 12 volt, which makes sense, because also under load it should be constant and regulated, that we always, under all conditions, that we always have the same bias current. So that really makes sense. But if we follow here along our let me see, it's a little bit difficult without having it on the computer, but we will get it handled. So, and that is what we have done before. So if we follow this trace here, right, we see that we directly get the bias supply out of our power supply, which is carrying 18 volt. So maybe they have corrected already in the amplifier, but have not yet, or what does that mean yet? I do not believe that they will change it in the future, because I do not believe that they still build these amplifiers. But anyways, I mean, so this is an error. Most likely here in our circuit, I believe that our bias circuit is also supplied by a voltage regulator, and well, so we have it different on the diagram, but we have seen that the input here is at 12 volt, so that makes it clear. So that means now we have to adjust our bias current with the 12 volt input, and then it should work. Okay, so let me switch it to transmit. Here we have it, and we read 1.6, 1.7 amps, so that is normal, because we see it increasing for a while, because our transistors are getting warm a little bit. Alright, so now let's see if we can adjust it, and we can. And as we said, we have to put it to 3.5 volt plus minus half an amp, 3.5 amps, of course, not volt, sorry, 3.5 amp bias current, and here we are. So that is just looking fine, no doubt. And let me once again check here my voltage at the input of the resistor, and where is it? 12 volt, yeah. So that is fine, and our current is still sitting here on 3.5 amps, so that looks fine. Let's go ahead. Yeah, and I've connected here a second hook to our remote socket to switch here the low pass filter relays. And if I go now here to ground, you can clearly hear that I'm setting here a pair of relays just to switch the right low pass filter for the right band through. And well, I've chosen here the left upper one because it was so easy to grab this contact over there. And that means here, according to our schematic, that is our 40 meter band, so we can test in the 40 meter band. Okay, so we are ready for testing. Here's our test setup, and yeah, we have here our LP-500 finally monitoring our output. But first of all, our amplifier is switched off, and I just want to check here my drive on SSB. So therefore, first of all, let's see with switched off. Let's see. 1 2 1 2. Hola. 1 2. Test test test. Hola. So that means, as you can see, we drive with approximately 60 watt peak. 1 2. Hola. Or maybe a little bit more. So that is our drive. And now let's prepare here our setup for our final test. I switch on my amplifier, and of course the second step is, let me go closer here to what we have, and of course I have to set now my amplifier into transmit, which we have done now. Back here to our DC amp meter, and you see our bias current is set right, so no doubt everything is fine. Now we really can try and see if our amplifier is working just fine. Okay, let's test. 1 2 1 2. Hola. 1 2 1 2 3. Hola. 1 2. Hola. So 550 peak. Let's see if I give a bit more drive. 1 2. Hola. 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 Yeah, you can see peaks over 600 watt, and that is just fine. Yeah, you really see what a simple potentiometer, a dirty pot, can really cause. So an amplifier which is drawing excessive current, and nobody knows why, and it is only, in brackets, a dirty pot. But yeah, you can't use an amplifier which is drawing such an excessive current, because you never know what really has happened to the amplifier, and you need to investigate it. So it was completely right that we had it in. Okay, so let's do a final test. So radio has been set to AM, that I get a carrier out of it, and that means a single tone. And let's see, now you see it is already in transmit, so we have our bias current. And now I set the radio into transmit, and let's increase here my output power, and you see now we have 400 watt key down with 50, that's it, 460 watt and we had approximately 50, what was it, 50 amp? You see, a little bit more, 470 with yeah, 56, or what is it? 54, 56 amps, and we get key down once again. Let's go over there that you can see it. Now increase it, and we get out of it key down 400. Yeah, that's it. 489 with 56 amps. So that is what we get out of it. Okay, so that's it finally. I mean, I will perform some intermodulation tests before the amplifier will leave here my lab. But yeah, I have some videos on if you're interested how intermodulation tests are performed. Anyways, this amp is fixed, and we can give it back. It was only, in bracket, a dirty pot, but yeah, it was a serious issue, and well, I hope you enjoyed it just a little bit. And yeah, if so, please give me a big thumb up. I hope you have learned a little bit about design, a little bit about yeah, amplifier design, and so that's it really for today. Bye, and catch you next time.